Is the video okay now? No, actually it was little blur. Good evening. Is the video okay now? Now see. Is it okay now? No. In case any problem is there, comment immediately because not up some time. Also, voice clear? Voice clear? Mic I put now. Now voice is clear? Okay, I'll start. See, new chapter. Oh, I had to control the volume here. Okay, now okay. Heading, deflection of beams. That means you can make a note. So far we consider strength aspect. Now tell me which aspect? Practical knowledge point of view. So far strength considered. See, I told you, when you consider axial force, shear force or bending moment or torsion and corresponding stresses all, it is actually strength factor, not strain. Okay, strain correct. But to be more precise, as per code, what is this one? Code language. As far as code language is concerned, strain nobody calls. This is called not deformation. Serviceability control. It is serviceability. That is deflection. This you can see. See, bending moment, shear force, axial force, stresses, strains all, you can't see. A strain sometimes you can see because you have to feel it. It is a ratio. That all you cannot see. But this you can see. See, serviceability means mainly deflection. In RCC, crack width comes. Vibrations. There, that all you can see. Why? It is visible for you. Okay, now come to deflection of beams. See, 1 minute now. We are going to start this chapter with the basic concepts. And all methods you don't require. Some standard methods you require and limited application, not that academic point of view questions. Because nowadays, if you want deflection, software will give it. When you prepare a model in software, it will give deflection. So you don't have to calculate it. But basic knowledge required. And you should know how to control the deflection and how the deflection is affected by span, loading, material, cross-section. Those things are important. Now, when you go to basic concept, that is called double integration method. Basic method is double integration method. Integration method. Actually, remember, this method has a drawback. This is an original method. So this has got drawback. For application, your struggle. I will show you how to your struggle sometimes. But same double integration method, a slight modification will make it very simple. Anybody can tell the name for that one? Double integration method, slightly modified. Macaulay's method. That will actually, Macaulay's method is nothing but double integration method only. So this we will solve only one example later, just to understand how is this method works. Macaulay's method is same, it is double integration only. See, now, when you derive the basic equation, so many places you can see d square y by dx square, and then they'll put secant square theta, tan theta all. That is called pure mathematical. That way you don't have to struggle. You are important to understand. So I told you this course is more and more practical oriented. So what practical aspect is there, I will take, because unnecessary waste of time I will not do. Okay, now I'll start. See, first remember, before starting, see, double integration method, other methods are there. This is modified later modified version is Macaulay's method. Spelling I don't know. Okay, Macaulay's method. Also we will study briefly, not briefly, a method called moment area method and conjugate beam method, and briefly strain energy method. This is using Castigliano's theorem. These all will study briefly. Limited application, because practically first of all any one method you use, and what beam you are considering in the class, simply supported or cantilever or overhanging beam, practically no frames will come there. Different member will have different cross sections, and in case of frames what will happen is loading will be odd, therefore that all software will give the deformation. But to understand correctly, these are all the methods we will study briefly. Everything not unnecessary waste of time I will not do. See, like the questions which are academic oriented, that I am starting separate class little later. I am planning to start deflection of beam systematically. It is pure theoretical. You can attend that one, but it will not be. It may be live class, not this course. But see now, before you start any of this method, I will remove. See, first randomly take a beam. See, suppose there is a simply supported beam. Apply any random loading. The beam will deform like this. This is the elastic curve. Elastic curve. Or if I take a cantilever beam, apply any loading, then elastic curve will come like this. Elastic curve. Or if I take a beam with overhang, apply any load. In case the overhang is not very heavy, the beam will deform. How? It will come down, then it will go up here, down. It may come random this way. Or in case the overhanging beam has heavy overhangs, then because of the heavy overhanging here, the beam may completely hog. It is possible. These are all elastic curve. Remember, elastic curve means deformed shape. Elastic curve means deformed shape, shape which you consider longitudinally. You consider longitudinally, usually a line diagram. Thickness all we don't show there. So the deformed shape, that line diagram, that line correspond to what? Neutral layer. Actually, if a beam deflects down this way, neutral layer, how much deflection? See, and actually the curvature will be, radius of curvature will be very huge. No. It will be what? Very huge. Therefore, the deformation for upper and lower will hardly matter. See, for example, if a beam bends this way, where is bending? Radius of center may be somewhere here. So, now what will happen is, how much this will come down, this will come down, or this will come down, all are same. See, this dimension of the beam is so small compared to huge radius. Okay, now further, what you do is, now see, now any one shape you can take a random shape now. See, first I will do one thing now, don't buy out sagging, hogging. See, imagine this is the original position. See, original beam. This is the initial line, initial position. Imagine the beam deforms here. How? It can deform anyway. Randomly I will put here. See, it comes this way, or imagine it goes this way. No problem. With respect to garment here, I will put central line here, initial position here. I will put randomly. Even this point is not support. It can come down. See, for example, this way, and see, it goes this way. Imagine. No problem. Now see here, any point you consider here, any point P, and clockwise I want. It's okay. Any point here, say for example, Q, randomly take it. See, this is the initial position. Initial position. The point P, which was initially here, now let it go to P dash. P dash is the final position. A little bigger I'll write here. This is P dash final position. Same way. This is the initial position. Initial position Q is here. This is the final position Q dash. Now, from the initial position, see, it came down. Here, it went up. And if I draw a tangent here, see, with initial beam axis, this should rotate here. Whereas, if I take a tangent here, then with axis, it will rotate like this. See, this is called displacement. This is called vertical displacement Y. Later, some people call Y. See, the deflection, most popular is delta, but for calculation, it is Y. Later you can put delta, but you cannot do, see, d square y by dx square will come. If you write delta, you are write d square delta. No. See, coordinate system, x and y. Therefore, x is horizontal, y is vertical. See, the point here, it came down here. Point Q, it went up here. This is y of the point P. This is y of the point Q. This is theta of point P, theta P. This is theta for the point Q. Now, therefore, YP at, see, for P, for the point P, YP is what? Displacement. Displacement means linear displacement. Remember, it is linear, like meter, millimeter, linear displacement from initial position. Initial position. That is what? It is the vertical for horizontal beams, which is vertical here. Vertical here. Suppose if a column is there, it will be horizontal. See, the YP, horizontal. And this YP is called, what, tell me? This YP is called what? How much the point will move. See, for example, I got a scale here. Okay, some scale I will take here. No problem. See. Initially, beam is like this. See now. Oh, now see. Now B point has moved here. Tell me what this is called. What this is called. How much it moves. That is a linear quantity. Remember, it is a linear. What it is called? How much it moves. That is called. Name. How much, that is a linear movement or linear displacement. This much difficulty. What it is called? First answer, because I want to confirm that everything is okay. If you don't comment, what will happen is, I won't be knowing if any problem is there. How much it moves here. This is technically called, what you are doing. No, if you don't reply, I am helpless. No, it is called, no, I told vertical displacement. Popular name. Okay, popular name I am telling. I wrote here vertical displacement. Popular name. Nobody will call that way in a question. Suppose a question given, what they will ask? Suppose what is what? Vertical displacement, correct. What is the popular name? Delta is symbol. Again, you are not. Popular name. Nobody calls it as vertical displacement or delta like that. What is the popular name? It is called deflection. See, deflection means linear displacement, called deflection. Deflection. Okay, now, same way at Q, deflection, and here YP is what? Down. See here, Here yp is down. Same way for q, yq is deflection. Deflection. As per sketch, here it is here that yq is upward. Why? See, here it came down, there it went up. That is combination. Just a understanding. Okay, now this is for deflection. So remember now, first one important. When you tell deflection, our symbol is y. Later you put delta. Y is always linear. Linear, like millimeter, centimeter, meter, etc. Okay, now same way, what is theta p? Theta p is angle made by tangent to elastic curve at p, or it is called angular displacement. P with the axis of beam. With axis of beam. See, axis of beam is horizontal here. It is called angular displacement. See, that is called linear displacement. This is called angular displacement or rotation. This is popularly called, this theta is popularly called what? Popularly called. Nobody calls angular displacement, rotation, popularly called. What it is? Popularly called slope. Slope. So, deflection is always linear displacement. I wrote here, linear displacement or displacement perpendicular to axis of beam. Axis of beam. And slope, symbol is y. Slope, y is called angular displacement. Angular displacement, or most popularly that is called slope. Remember, angular displacement means, or you can tell one more thing, it is how much is rotation. Rotation. See, it is this way, angular. How much is rotation? Unit. This should be angular. Degree or radian, etc. Gradient is not used now. Degree or radian. That is general language. But usually, if you want to tell somebody outside, you are tell deflection in millimeter. Why? You tell meter, point not something, people won't understand. You tell in radians, no, he won't understand. You should tell turned by, rotated by 2 degrees, 1.5 degrees, etc. Okay, now, one most important, I will tell now only. See, I will tell now only now. Most important. See, mathematics. See, now, when a beam deflects, practically, can you see the deflection? Tell me. Can you look at the beam and see the deflection? If you can see the deflection, you will not stay in the building, first of all. You will run away from the building. Can you see the deflection when you look at a beam? No. That means deflection is small. And rotation. Can you see rotation? First of all, tell me. Can you see rotation? Can you see rotation? No. Rotation also not visible. Therefore, see, the deflection, usually for a span of, for example, some 6 meter span, I will tell you deflection Y maximum is 12 millimeter. For a beam of 6 meter span, big span, 12 mm, see this much. It is there. You cannot see it. 100% not visible. Not visible. So, the beam which is straight earlier almost looks straight only. You can't make out. Or, suppose this is the beam. You measure horizontally. If it is 6 meter, suppose the beam bent this way, exaggeration. You take a tape along the deflected curve. Tell me how much measurement will come. This measurement made this way along the curvature. First you measure horizontal distance, span, before deformation. Then after deflection, under the beam, put a tape. Then how much? Almost equal to what? You cannot make out. Very minute, 6.00 something. Or 6, for example, randomly, 6.002 meter. Ayyo, they will tell 6 meter only. Correct? Therefore, if you look at the, see, if the horizontal span considered 6 meter, if you look at the beam, see the length of the beam along the curvature, it is also, you can tell nearly 6 meter only, slightly more. Slightly more. Clear? It is slightly more. Okay. Now, therefore, remember one important, and angle theta. How much? Maximum theta. See, theta maximum. Just, can you see 10, 12 degrees? Tell me. 10 degree, 15 degree. Possible? See, 10 degree, 15 degree. Possible? First of all, tell me. Can you ever imagine some 10 degree, 15 degree, 30 degree like that? Can you imagine a beam where you can see turning 10, 15 degrees? Possible? Outrightly not possible. Little, say for example, say usually it will be less than 1 degree. It will be less than 1 degree. Or say it is 1.2 degrees randomly. 1.2 degrees. Just take randomly. Usually, if for RCC beam, it will be further lesser. Why? High fluctuativity will be there. Any beam, timber beam, say 1.2 degrees. Okay. Now, since this angle is very small, remember 1.2 actually is not very small. Actually, it will be what? Say, usually you get 0.4 degrees, 0.5 degree like that. Okay. Even if you take 1.2 degrees, then you know mathematically what? You know mathematically practical purpose. I have told you, I am not wasting time on going for the curvature, elemental length, putting d square, dx square plus dy square equal ds square. So ds equal root of dx square plus dy square, or dx root 1 plus dy by dx whole square. Then finally write everything. You can see textbook solve. They write all those things. Then they will tell the term dy by dx compared to 1 plus dy by dx square. That second term is so small, can be ignored. Therefore, they will tell finally equal to 1 only. That we will make in the beginning only. Why waste time? Why unnecessarily go for complication? But remember, if you are going for pure theoretical, you have to go that way. That I will do in the other class. Okay. I decided to take up deflection in some classes will be there, live class only I will take, but timing will be given on the same day. Whenever I am free, I will create a live class per day, not more than 1 hour. You can attend that one and learn more and more basic if you want. It will be very long procedure. Why? All cases will be covered there. It is somewhat academic oriented. Okay. Now, since mathematically you can tell when theta is very small, you can tell tan theta equal to theta. Tell me, yes or no? You can tell tan theta equal to theta. Mathematically, see, when theta is very small, you can take tan theta equal to theta, sin theta equal to theta, but not cos theta equal to theta. Cos theta equal to 1. Clear? Okay, now, take your calculator. Take your calculator and tell me what is tan of 1.2. Tell the answer. What is tan of 1.2? Fast. We will check now only. No doubts later. Tan 1.2. Tan 1.2. How much? Tan 1.2. Actually 1.2 is very small. Answer fast. Tan 1.2. So When you tell tan theta equal to theta means when you take tan of 1.2, you should get back theta answer only. Tell me, what is tan 1.2? Just imagine, for understanding, theta is 1.2 degrees. First, take calculator. Calculate tan 1.2. Point not 20947. That is, so therefore, for 1.2 degrees, will tan theta will come theta? Tell me. Will tan theta will come theta only? Or full difference is there? Tell me. For 1.2 degrees, tan theta, is it coming equal to theta or something else? Tell me. Is it coming theta only or something else? Practically 1.2 degree slope will be there. So many times 1.2 degree slope is there. Tell me, when you take tan 1.2, are you getting 1.2? Actually, as per my statement, when you take tan 1.2, you should get back 1.2. But are you getting? Tell me, are you getting? You should clarify now only. No. If I take tan of 1.2, tan theta, answer should come theta only. Calculate should tell 1.2. It is not giving 1.2. It is giving 0.020947. So for 1.2, tan theta equal to theta is wrong. Yes or no? For theta only. For 1.2, tan theta equal to theta is wrong. Yes or no? Tan theta equal to theta is wrong. When you press tan, number should not change. Yes or no? 1.2 degrees, tan theta is not equal to theta. So much of difference. See, 1.2 and 0.02. Where is it? You are not answering. Yes or no? For 1.2, you cannot write tan theta equal to theta. Tell me yes or no. First. For 1.2, you cannot write tan theta equal to theta. You are not answering. Tell yes or no. We cannot write. You are wasting time by not commenting. See, this is the problem. Unnecessary waste. That's why these classes causes problem. If you don't answer, one, I want it to be clear. Second, there should be no trouble regarding voice solve. How much you have to wait? If this way, if you don't answer, what? I can't do anything. I told just now, I am telling 100 times now. For 1.2, you cannot consider tan theta equal to theta. No, see, usually people answer. First of all, this statement is nonsense. Remember. So make a note. What note? Tan theta equal to theta is valid for small theta, but condition is there. Condition, theta should be in radian. Degree not allowed. First of all, in structural engineering, in deformation, degree is not allowed. Clear or not? First, don't delay. Degree is not allowed. Theta should be in radians. Remember, but then why you told the answer 0.0209? See, when I take tan of that one, 0.0209 came. It looks 0.020947 came. Theta should be in radian. Clear or not? Clear. Therefore, when I tell tan theta equal to theta, I told 1.2 degrees a common angle for any beam. So if it is not satisfied, I should quit teaching. Why? I told you tan theta equal to theta and it is found to be wrong. Such a mathematical blunder if I make, I won't continue. So deliberately I was telling. So what you do is, if it is 1.2 degrees, okay, take in radians equal to 1.2 into pi by 180. Tell the answer. 1.2 into pi by 180. What is the answer? Or one thing, what you have to do is 1.2 into pi by 180. What is the answer? 1.2 into pi by 180. Tell the answer. 1.2 into pi by 180. Answer. 0.20947. Oh, Udgara. Therefore, correct or wrong? Now you are getting tan theta equal to theta. See, same answer. Yes, I will not make such mistakes. Therefore, remember 1.2 degrees, even 2 degree, 3 degree also it will come same. First of all, for small angles, therefore, make a note. In the entire structural engineering, when deformation is considered, theta or any angular measurement angle should be in radians. Degree not allowed. So when you solve, you will always get in radians. Later, for presentation, you can go to degrees. Suppose you get answer, a beam slope 0.02. See how much answer I told? 0.02 radian you got. You tell somebody how much your beam will rotate. 0.02 radian. He will tell 0.02 radian. What is radian? I don't know those things. Oh, then you tell him in degrees. You multiply by 180, divide by pi, and tell me nearly to 1.2 degrees. Then you will understand. But structural engineering, remember, when you take tan theta equal to theta, see, when you take tan theta equal to theta, and also later ds equal to rd theta, remember or not? Arc length ds, if the angle is d theta, if it is radius r, arc length equal to r into d theta. This also you are taking. Arc length equal to radius into angle at subtended at center. That is valid only when theta is in radian. Full clear? Valid only when theta is in radian. Fast. Clear or not? It is valid only when theta is in radians. Degree has no entry for deformation calculation. See, when you resolve the forces, it is not deformation. Sin 30, that's okay. There you can take degree or radian, whatever you want. But when deformation comes, it should be in radian. Okay, now start. First come to basic differential equation for, we will consider basic differential equation. Some people will call Bernoulli's equation. Euler-Bernoulli, not required. See, basic differential equation for slope and deflection. Okay, start. How to start? Imagine a beam. See, some beam here, initial position, cut. Apply any loading. Beam will deform like this. This is the elastic curve. Consider 2 points on that side. Remember, we will consider sagging beam. Very important. Sign also counts here. Be careful. We will consider beam is sagging. Take 2 points, say 1 and 2. 1 and 2 are very near. Very near to each other. At horizontal distance of dx, at a distance of x from here, a distance of x from origin. Somewhere here you take origin. Where? Anywhere you take origin. From origin you consider distance x. Then along x, 1 and 2. Actually, remember now, actually I will tell you how is that one. See, if the beam deforms this way, 1 is here, 2 is here. Clear? If 1 is here, 2 is, dx means what? Very small. 1 and 2 you can't make out. It is infinitely small. Clear? Here exaggeration. See, here exaggeration 1 and 2. And if you consider bent shape, this is center. O. Origin I will call O. This I will call O dash. This is radius r. Radius r. See, for this beam, see, actually it will be so high that you can't make out. See, for example, if the beam bends like this, radius will come somewhere here. You can't imagine. I told you, radius for a beam, as the bending is lesser, radius is very heavy. That is what? Very high radius means curvature is lesser. This all I told you in bending stress chapter. So 2.192 exaggerated. Okay, now you further exaggerate. Further exaggerate. See, you consider only 1 and 2 this way. Randomly exaggerate. See, this way exaggeration is not possible. I will put here now. See, this way. Exaggerate further. 1 and 2. Remember, actually, if 1 is here, 2 is there only. Now, this is the center. If it is an arc, center O dash, and this radius is R. Now, draw a tangent here to elastic curve. Let this angle be theta. Draw a tangent here. Now, let this angle be d theta. From here to here, at the center, it turned by d theta. Anybody can tell what is this angle? Fast. If this is theta, one more thing now. When I measure from origin x this way, when you take sagging beam, your theta is measured in anti-clockwise direction. I all will tell you. If this is theta, if this is d theta, tell me angle here. Okay, I won't waste time. It is theta plus d theta. First of all, theta is very small. Theta plus d theta is same. If it is, say, for example, degree, 1.2 degree. This is 1.2000000000001 degree. So this is exaggeration. Okay, now elastic curve go this way. This much clear? Fast, tell me. This much clear? This much clear or not? This much statement clear? Now we get simple equation. I remember, once I get the equation, I will explain, I will change the way I am explaining. It will be a systematic approach. This much clear? First. Okay. Now, what you do is theta plus d theta. Now see, this all I will remove now. See, I remember now, I took x this way. Origin is here. I consider sagging beam. And one more thing. See, this horizontal length here between these two is dx. And this arc length here, arc length is ds. And this is 0.2 from 1 is vertically upward by very small dy. See, if I consider 2 with respect to 1, see, if I consider 2, if 2 considered with respect to 1, then dx is horizontal length and dy is horizontal vertical displacement, and d theta is what? Change of slope. And vertical displacement I take upward, x I take right side, d theta I take anti-clockwise, and bending moment considered sagging. This I will tell you one by one. Okay, start. Now, simple. We know that, sometime academic class, I will tell them, knowing or not knowing, I am writing, you agree. So some people tell, yes sir, we know it sir. Good. We know that dy by dx is always equal to, let the answer come. If you tell the answer, over. Dy by dx is always equal to, you should know that much mathematical knowledge required. Dy by dx is always equal to, first, I am waiting. Dy by dx equal to, mathematics. First. Dy by dx equal to tan theta. But tan theta can be taken almost equal to theta in radians. I told so many times. And also dy by tan theta. Therefore, see, tan theta equal to theta. Therefore, your dy by dx can be taken equal to theta. But remember, theta in radians. One aspect over. Second one, we know that ds equal to r d theta. Yes or no? Arc length equal to radius into d theta. Yes, clear or not? Arc length ds equal to r into d theta. Yes or no? ds equal to r d theta. Arc length equal to angle at the center into what? Radius. Okay, now, therefore, ds by d theta equal to what? ds by r. I want d theta by dx. Therefore, d theta by dx equal to what? D theta by dx equal to ds equal to d theta by ds equal to 1 by r. D theta by dx equal to 1 by r. Okay, now if I go further, theta equal to dy by dx, d theta by ds, but also you know that ds is almost equal to dx. What people do is they will take ds equal to square root of dx square plus dy square. Then they will write, see, ds equal to square root of dx square plus dy square, or they will write root of what? Dx, they will tell dx square by dx square, then further plus dy square by dx square, or they will take what then? Or they will tell what? Dx outside, then they will tell 1 plus dy by dx the whole square root. They will write this way. Later they will tell this term is ignored. But therefore, why waste time? See, I already told you, for a beam, if you measure along the, you make a note here, if you measure horizontally, what length you get? Suppose you go through elastic curve, are you getting same length or not? Here exaggerated. See, ds, you make a note here, dx is measurement horizontally made. ds is measurement made along the curvature. Both are what? For a beam, if you see, if you measure horizontally or along curvature, both are almost what? Both are almost. No difference. I told span 6 meter. Measure through what? Curvature. 6.001 meter. For elemental length, both are almost equal. So what you can do is, we can put ds almost equal dx. Therefore what? D theta by dx equal to 1 by r. D theta by dx equal to 1 by r. Clear? Yes or no? D theta by dx equal to 1 by r. Okay, now this is dy by dx equal to theta, d theta by dx equal to 1 by r. Or you can tell, 1 minute, I will remove this one now. This I will remove now, not required. See, and remember, before I remove, make a note, the derivation I have done, x to right side, origin is on the left side, and dy is taken up, dx is taken to right side, theta is taken anti-clockwise, and bm is sagging. I will tell once again later. See, you got dy by dx equal to theta. Now, dy by dx equal to theta. Differentiate earlier equation, earlier one. Differentiating d theta by dx equal to d square y by dx square. Yes or no? See, I'll do one thing. This I will call equation number 1. This I will call equation number 2. This 1 and 2 is not that 1 and 2. Okay, now differentiate 1. dy by 1, that is what? dy by dx equal to d theta. You get d theta by dx equal to d square y by dx square. But we already got d theta by dx equal to 1 by r, that is equation number 2. Therefore, see, d square y by dx square from, therefore we can write what? D square y by dx square equal to 1 by r. Tell me, fully clear? Very simple. See, 1 minute, I'll tell once again. dy by dx equal to theta, mathematical. Differentiate it. d theta by dx equal to d square y by dx square. Okay. Keep it aside. Okay. Wait for some time. Hey, you wait for some time. Chukke. One dot. ds equal to r d theta. So d theta by ds equal to 1 by r. But ds you can take almost equal dx. So d theta by dx equal to 1 by r. Okay. Now, one more dot. Double dot. From this is d theta by dx equal to 1 by r. D theta by dx equal to d square y by dx square, equate d square y by dx square equal to 1 by r. Further not required. Clear? Fast. Clear or not? Tell me clear, I will go further. Clear? Fast. If it is clear, I will go to the next step. Clear? Okay. Now, let you tell it equation number 3. Okay, wait for some time. Okay, now let m suffix x be bending moment at x from origin. Then we have the basic equation m by I equal to e by r, or your 1 by r equal to m divided by ei. Here 1 by r equal to m at the point x by ei. Why? Because at this point bending moment is mx. So this is equation number 4. See, we already got 1 by r equal to d square y by dx square. M by I equal to E by R. So 1 by R equal to M by EI, or 1 by R equal to M means bending moment is MX by EI. Now lastly, from 3 and 4, you can tell d square y by dx square equal to mx divided by ei, or I will use a color now. Why? We came to the concluding part, some other color. Okay, blue color will do, not red. Okay, red color will do, red color, or cross multiply, or ei d square y by dx square equal to bending moment m at x. This is called basic differential equation. Basic differential equation for slope and deflection. Actually, slope has not come. Equation for getting slope and deflection. Tell me, full clear means I will go next step. d square y by dx square equal to bending moment suffix x mx. Which point you consider there? bm by ei. First, clear? ei d square y by dx square is mx. I will explain the term ei also. What is the meaning of ei? Clear? Okay. Now, what you do is, this is the equation. See, just see now. Integrate. What you get? You get ei d square y by dx square. If you integrate, you get dy by dx. equal to integration of mx into dx with respect to x. Now, you know that dy by dx is tan theta. You also know that further tan theta equal to theta. Therefore, this term dy by dx is theta in radian. This is called slope equation. Slope equation. Using this equation, you can find slope. Now, integrate once again. Integrate again. What do you get? Ei dy by dx, if you integrate, you get y. Y at any point x. This is at any point x. Y, theta at x. Okay, tan theta x. Yx equal to integration of mx into dx. Now, this y at x is the deflection. Therefore, this is called deflection equation. When I make application, everything will be clear. Deflection equation. See, integrate once, you get the slope equation. Successively, second time integrate, you get deflection equation. That's why the method is called what? Tell me. That's why this basic, remember, this is the basic method. Any other method you do originates from here only. There is no method where this is not used. Moment area method or conjugate beam method. Yeah, all everywhere. Remember, they start from here, but then here you go for equation. There, some bending moment diagram will be used. That is some imaginary concept will be there. But remember, each and every deflection part originates from basic differential equation. So that's why method is called what? Method is called double integration method. Method is called double integration method. Integration method. Okay, now sign I will tell you later, 1 minute now. Now, I will first tell some more thumb now. See. Now, observe correctly or observe. Observe. See, common sense will do. Anywhere, theta and y. Tell what you get. See here. Anywhere you want theta, anywhere you want y, it will have numerator, what? Bending moment parameter is there. Connected with the bending moment parameter is there. Tell yes or no. See here. Ei dy by dx is theta equal to bending moment parameter. Not bending moment. Integration. Something which is to do with the bending moment and span. Bending moment and span. Why? When you integrate, span will come. So the numerator has something to do with the bending moment and span. Correct? Bending moment and span. Tell yes or no. The numerator, see here, you take theta equal to integration mx. This you take other side. So how much beam is rotating or how much beam is deflecting, in the numerator, bending moment and span term will be there. Yes or no? Yes. Whereas, tell what will come in denominator. Fast. What will come in denominator? Fast, tell me. What will come in denominator? Throughout, not only here, whether you do by double integration method or Macaulay's method or conjugate beam method, moment area method, then strain energy method using Castiglio's theorem, unit load method, any method, whatever, whether stiffness method, flexibility method, any method you do, denominator will be Ei. Therefore, see, theta and y are actually deformation. Deformation means theta is the angular deformation, y is the linear deformation. See, they are deformation. Therefore, tell good or bad. Therefore, tell good or bad. Slope and beam rotating too much or deflecting too much. Good or bad? Good or bad? Good or bad? Bad. Okay, bad. And the bad terms are in what? Tell me. The bad terms are in where? See, as you have more and more span and as you apply more and more load, surely BM will increase. See, sorry, bending moment, span, loading also is there. When the bending moment is there, span and loading both are there. See, apply more and more loading. Have a high span. Tell me, what will happen? You have high span more, span increases and loading increases. Loading increases. In both the cases, slope and deflection will also what? Slope and deflection will also, if you have high span and heavy loading, slope and deflection will also, first, slope and deflection will also increase. Will also increase. This is bad. Bad, but we are helpless. Why, tell me? We are helpless. Why? Tell me. Why you are helpless? When you go for a beam, span is already fixed. You can't change the span. Loading also already fixed. You can't tell, apply lesser load. How? Whatever load comes, load will be transferred. And span you are helpless. Therefore, numerator is not in our hand. This numerator is right. Numerator, which is actually bad, is not under our control. Under our control. Suppose someone will tell, I want a steel beam to be designed for a span of simply support span of 8 meter loaded by 60 kN per meter. Yes, you can't do anything. You have to design for a span of 6 meter, UDL of 60 kN per meter. Whatever BM comes, it should be able to resist. Whatever shear force, it should be able to resist. So, it is not our control. But, adare, I will remove this one now. But, the denominator term, that is EI, it is in the hands of structural engineer. Of course, E is constant, material constant, I, structural engineer. See, I is moment of inertia of cross section about neutral axis. This is in the hand of structural engineer. A structural engineer can provide smaller section or bigger section. Therefore, I told you 1,000 times, structural engineering is always cross section. Therefore, numerator is not in our hand. We are helpless. But denominator is under our control. So therefore, the term EI, now tell me correctly, EI term comes in denominator. See, your EI comes in denominator. Therefore, as EI increases, or first of all tell me, the term EI has a name. It is the product of, see, the term EI is product of modulus of elasticity of material of the beam and moment of inertia of cross section about neutral axis. This is in the hand of the structural engineer's control is here. Structural engineer's control is in I. So now tell me, as EI increases, 1 minute, forgot, and this term EI, anybody can tell what is the name for EI? If you know it correctly, EI is called flexural rigidity of what? 99% people, they will tell flexural rigidity of the beam. No, wrong. It is not depending upon length. So it is called flexural rigidity of what? Of cross section. I told you this is cross sectional property. 99% people don't use this word. They will tell EI is flexural rigidity for the beam. I will tell them for the beam. Depends on length. No. Then why you told for beam? You tell it is flexural rigidity of the cross section of the beam. Cross section of beam. Now tell me, EI is good or bad? Tell me, EI is good or bad? First, by name only you can make out. See the hand now. Flexural rigidity of the, by name only. See, when you tell loading, load more, span more, bending moment more, we cannot do anything, helpless. See, desperate feeling. See here, EI is, how you tell somebody? It is flexural rigidity. See here, of cross section of the beam. So EI is good or bad? EI is good. Good. So therefore, tell the answer. As EI increases, then slope and deflection both, that is deformation or serviceability condition, what will happen? As EI increases, slope and deflection both will decrease or reduce. Therefore, good. Why? We do not want heavy slope and deflection. Danger. When you look at the beam, see the rotation, see the beam turning there, see how much it came down. I am not coming to building. They will tell, I am going away. I don't want to come to this room. That beam has already bent by around 4-5 inches. I don't know when it will fall down on my head. So theta will decrease. Good. That is why it is called flexural rigidity of the cross section. See, your numerator is like bill in the hotel. Denominator is like how much money you have got. See, numerator, bill, eat more, pay more, bad. Denominator, what money you got, good. Therefore, EI, or remember, as EI good, therefore beam becomes more and more serviceable. Correct? The serviceability will be controlled. You write yourself only. If EI is more, then you can achieve the serviceability requirement. That is, serviceability means controlling of deformation. Serviceability means what? Controlling of deformation. Deformation to be controlled. Yes. Okay. Now, make a note. As EI reduces, see, that is, moment of inertia reduces, beam becomes smaller cross section. Good or bad? Beam, see, the beam, see, one of my beam, that beam has fractional rigidity of 25,000 kilonewton meter square. What about that beam? That beam section is not sufficient. Due to some reason, they are given a smaller section. Its rigidity is only 8,000 kN per meter square. See, one will tell, I have 25,000 rupees with me. Someone will tell, I have only 8,000 with me. Good or bad? Bad. Therefore, remember, lastly, your slope and deflection is proportional to what degree later? Proportional to load, span, etc. Means bending moment, etc. So, whereas it is inversely proportional. Inversely proportional. Proportional to EI. EI means flexural rigidity of the cross section. So, flexural rigidity of the cross section is what? Is the product of Young's modulus of elasticity of the material, if E is more, good, deformation is lesser. And also moment of inertia. Here you consider material and cross section. Material and cross section. Full clear? Fast. Tell me. Full clear or not? We will go systematic way. Full clear? All these aspects. Okay, now before going further, I want to make one thing clear now. I can make it later. No, right now, next class onwards, it will be your problem. Make a note. Why? Because now time also is not much. I can't go to integration now. So therefore, one important portion I will tell now. See, note. Note. When we substitute for EI in the expression for slope and deflection, we should consider same units considered for loading and span, that is, which comes in numerator. Same thing. And usually means generally, almost 99.9% case, when we consider analysis for deflection and slope, we consider kilonewton and meter for loading and span. Yes or no? For loading and span. Nobody will tell a beam is of span 4000 millimeter. No. See, like bending moment. See, stresses and strains, we take newtons and millimeter. But when you go for bending moment shear force, you go for kilonewton meter. Later for design, you convert to Newton millimeter. See, 10 to the power 6, 10 to the power 3. Same way here. When you solve a problem, usually you consider kilonewton and meter. Therefore, EI should also what? For EI also same basic units to be considered before substituting. Now remember, E is modulus of elasticity. Dimensionally E is force per distance square. This I told you long back in stress strain chapter. I won't repeat. Like Newton per mm square, Newton per centimeter square, kilonewton per meter square, etc. And I is linear power 4. Like, see what? Example, Newton per mm square, Newton per centimeter square, or kilonewton per millimeter square, or kilonewton per meter square, anything. I, linear power 4, like millimeter power 4, centimeter power 4, meter power 4, etc., etc. Therefore, dimensionally, your EI will be force per distance square. That is your E. And linear power 4, that is your I. Or dimensionally EI is force per distance square into L power 4 is force into L square. Not force per L square. Wrong. Make a note, like example, like Newton millimeter square, kilonewton millimeter square, meter square, or Newton meter square, or kilonewton millimeter square, anything. It will have force into it. Or remember, force into distance square. Distance square. So when the term E is there, it is force per distance square. I is distance power 4, linear power 4. But EI product, flexural rigidity is always force into distance square, not per. Sometime in the class I will tell, when you tell E, per will come. But Newton per mm square. When you tell I, linear power 4. When the EI comes, if you use the word per, I will come to you, I will take your book and see, per. ಕನ್ನಡದಲ್ಲಿ ಪರ್ ಅಂತ ಹರಿದಾಕ್ತೀನಿ ಅಂತ. See, this way, per, I will tear it and throw it outside. I give warning. Sometimes students will tell, how much EI? Sir, 20,000 Newton kilonewton per meter square. What? Kilonewton per? Sorry, sir. Per should not come. The word per should never come when you consider the term EI. Clear or not? No more warning. In future, sometime deliberately, I will write per. Student will tell, sir, no per. Then I will tell him, who told you? Sir, you only told you. Okay, I wrote deliberately. Because even in MTech papers, I have seen giving EI in Newton per mm square or kilonewton per meter square. I don't know how much basic knowledge he is having. Somebody giving EI kilonewton per meter square needs. I don't want to comment further. Sorry. That I can, sometime I have seen MTech paper, moment given in kilonewton per meter. See, some will tell, hey, it is a print mistake. I will tell, no, print mistake is okay. You see, what is the time now? 8:40 p.m., 8:50 p.m., okay, 8:30 p.m. I cannot tell 6 a.m. or 10 a.m. If I tell 10 a.m. or 8:30 a.m., morning 8:30, I don't have common sense. Evening 8:30, 8:40, I don't know time now. I'll see a time now. See, 8:49 p.m., okay. That is called a little error. But telling that time now is 8:50 a.m. morning, a.m. p.m. confusion, okay. Morning 8:30. What someone will tell? Is it morning 8:30 in India? So therefore, it will be morning 8:30 somewhere else. In India, it is not morning 8:30. All of you are for everybody, time is around 8:50 p.m. Okay, now, right now, final conclusion. Just imagine. Example is solved in kilonewton and meter unit. Like that is maybe a beam of span, say 8 meter, loaded by UDL of 60 kilonewton per meter and a point load of 100 kilonewton at a distance of 2 meter from here. This is 5 meter here. That is, problem is solved in kilonewton meter. These all will come to numerator. Clear? These all will come to numerator. Clear now? These all will come to numerator. Clear or not? These all will come to numerator. I want clear or not? This everything come to numerator. Okay, now, therefore, here we need EI in what? In kilonewton. I will ask the students, per what? Sir, no per. Good. Kilonewton meter square we want. Okay, now, suppose the question is in Newton and meter. You want EI in Newton meter square. That I can't tell. Suppose for some reason problem is solved in newtons and millimeter. We want EI in Newton millimeter square. That is rare case. 99.9% we are solving in kilonewton and meter. So EI also in kilonewton meter square. Now examples. Example, ನೋಡಿ. Example 1. Suppose given in the question, E equal to 200, E equal to 200 kilonewton per millimeter square, and I equal to some 60 10 to the power 6 millimeter power 4. Question, they can give any unit. See, you can't tell the person, I am solving in kilonewton. Why are you giving in Newton? I am solving in meter. Why you give in millimeter? I will give whatever I want. You convert it. Okay. Now, use this data. We need EI in kilonewton meter square. I will tell you answer. I will tell you the answer. You will correctly calculate. EI will come 12,000 kilonewton meter square should come. Example 2. Suppose given, ಒಂದು ವೇಳೆ ಕೊಟ್ಟರೆ, suppose somebody given, E equal to, in question, E equal to not 200. Why always 200? I will take RC section. 200 by 10 is 20. 20 GPA, or not 20, 18 GPA. Why means don't bother. 18 GPA and I equal to, deliberately they are not giving millimeter, they will tell I equal to 12,000 centimeter power 4. See, troublemakers. Then also we need EI in kilonewton meter square. I want answer. $2160 kilonewton meter square is the answer. You have to get this answer now. Okay, fast get the answer. I will explain on the board. Today only I will explain on the board. But before that, see, for non-stop talking, now what time now? Not much time left now. 8:54. Okay, do one thing. 8:54 means it will take beyond the limit. 5 minutes earlier. Okay, do one thing. Tomorrow I will explain this one. But by that time, you get these two answers. You get these two answers. You should get these two and tell, you type, yes, I got. I will check second time. 1 minute. Second one, I will check once again. Yes, correct. 2160. You should type now, yes, got it, good. Anyway, everybody may not get it. Therefore, tomorrow class, as I start, I will explain these two in such a way that it 100% it will be clear. And then onwards, I will tell in the class, now onwards, when I solve any problem, I can give E in any unit, I can give I in any unit. I will not explain, I will tell you solve yourself and get EI this much, this unit. That is your problem. I will tell given data, therefore use your common sense and mathematical knowledge, convert EI, get it in required units. I will explain these two. If you got, you can tell got it. Okay. Suresh has told, first I got. Get second also. I will wait for the class. Another 4 or 5 minutes, I will wait here. I will not disconnect the class. Another 4 or 5 minutes, I will not disconnect. I will disconnect after 5 minutes. Okay. So before 5 minutes, I want at least some comments that, yes, answer came. If you got the answer, log out. You go for your dinner if you got the answer. Otherwise, get it. Anyway, tomorrow I am explaining once again. Don't worry.